We've already seen one gas law that deals with two of these variables and their relationships. That's Boyle's law, which has to do with pressure and volume. When volume and the amount of moles are held constant, we can look at the relationship between pressure and temperature, and that is Guy-Lussac's law. Guy-Lussac's law tells us if the amount of gas and the volume of the container are held constant, the pressure of an ideal gas is directly proportional to the temperature of the gas. Guy-Lussac explains something that you've seen before. This warning label. Do not place in hot water or near radiators. Protect from sunlight. Do not expose to temperatures over 120 degrees Fahrenheit. You do not want this to get warm because as the temperature increases, particles with more kinetic energy collide with the container walls more often, increasing the pressure. You don't want pressure to build up because you'll get an explosion. This is how Guy-Lussac's law can be described in an equation. We can write that like this. And the equation that we'll be using looks like this. This helps us calculate the pressure or temperature of a new state as long as volume and number of particles remains constant. Here's a problem where we can use Guy-Lussac's law. A scientist measures the pressure of a particular gas in a closed fixed volume container. We have the pressure, 1.25 atmospheres, and we have the temperature, 20 degrees C. So we know this side of our equation. It's just going to be a number. The scientist then heats the container to a temperature of 75 degrees C. So we have the final temperature. We could solve for pressure too, or final pressure, the new pressure of the system. Before we can do that, we'll have to convert the temperature to Kelvin. Here we have the given information. We just have to solve for P2. So we substitute in P1, T1, and T2. That would be 293.15 Kelvin. $348.15 Kelvin. You take this, multiply 348.15, and you'll solve for P2. Temperature's increased, and so has our pressure.